Hi, my name is Junyo Lee, and I'm presenting our recent work, Real-Time Video Deblurring via Lightweight Motion Compensation. This is joint work with Hyung-Suk Song, Sung-Hyun Cho, and Seung-Young Lee from Postec. Video deblurring aims to remove motion blur, which can be easily found in videos captured in dynamic environments including camera shakes or moving objects. For successful video deblurring, it is essential to utilize temporal information from neighboring frames. The figure in the slide shows the typical case of leveraging motion compensation for video deblurring. Given blurry video frames, we compute the motion between the frames and align them, which are then fed to the deblurring framework. With motion compensation, the deblurring quality increases as the deblurring framework can easily utilize temporal information of neighboring frames. For an effective aggregation of temporal information, many approaches align neighboring frames or their features by adopting a separate motion compensation module, such as optical flow, a spatial transformer network, dynamic convolution, and deformable convolution. However, while motion compensation improves the deblurring performance, as shown in the blue circles of the figure, heavy computation is required to align blurry frames, which causes significantly increased computational time, model size, and memory consumption for video deblurring. As can be found in the green circles of the figure, some approaches pursue efficiency over deblurring quality by omitting the motion compensation module. Nonetheless, these methods can still not perform real-time video deblurring because a large network capacity is demanded not only for deblurring, but also for aggregating useful temporal information from unaligned blurry frames or features. We aim to resolve this cost problem when employing motion compensation for deblurring. We propose a real-time video deblurring framework consisting of a lightweight multitask unit that supports both video deblurring and motion compensation in a harmonious way. The key component of the proposed framework is a lightweight multitask unit that simultaneously handles large portions of the deblurring and motion compensation tasks using a single shared network. To maximize the efficiency of our framework, both deblurring and motion compensation tasks need to take full advantage of the shared network in a harmonious way. However, we found that each task requires different natures of features, which limits the direct sharing of features. For the deblurring task, we need to extract detailed information from a degraded input for high-quality deblurred results. However, for the motion compensation task, we observe that the structural information is required in addition to the detailed information. Specifically, for restoration tasks including deblurring, extracting detailed information from degraded input has shown to be effective in achieving high performance, for which residual detail learning has widely been adopted. However, for the motion compensation task, we observe that the structural information of a degraded input is required, in addition to the detailed information. The following figure shows our preliminary experiment that shows alignment results using features of different natures. The alignment results using detailed features shows that details in residual images do not provide enough information for accurate alignment. However, features combined with the structure and detail information show more accurately aligned results. Hence, if we naively set up the multitask unit, the shared features will not be fully exploited for both the deblurring and motion compensation tasks. For the deblurring task, the deblurring network is trained to produce a residual image for deblurring, which induces the multitask detail network to produce detail features. On the other hand, the motion compensation task, which requires additional structure information, will induce the shared features to include structure information. This will hinder the multitask detail network from producing detailed features, and it will limit the deblurring performance of the network. To avoid this, we need a multitask network that extracts shared features that can work for both the deblurring and motion compensation tasks in a harmonious way. To this end, we propose the multitask unit with the structure injection scheme. We first make sure the detail level features are extracted from the multitask network and utilized for the deblurring network. For the motion compensation network, we combine detail level features with structural features that are pre-computed from blurry input frames using a convolution layer. The proposed multitask unit with the structure injection scheme improves the feature compatibility and minimizes the cost of incorporating motion compensation into video deblurring and enables real-time deblurring. In the next slides, we will delve into more details about each network. In our multitask unit, the multitask detail network F computes a multitask detail features shared by the deblurring and motion compensation networks. The multitask detail network is a lightweight network based on the UNet architecture and has most of the learnable parameters of the multitask unit. The deblurring network D consists of the one convolution layer named the deblur layer. The network transforms concatenated detail features of the current and previous frames to an output residual image. Distinguished from the previous works leveraging a heavy motion compensation module, our motion compensation network M is extremely fast as it shares the network capacity for feature extraction with the deblurring task. It only requires a single convolution layer, named the motion layer, to constitute the structure-injected features. Then a simple correlation-based motion compensation module with non-learnable operations aligns previous structure-injected features to the current one. To train the network, we use deblurring and motion losses. The deblurring loss is defined using the L1 norm between the deblurred and ground truth frames. The motion loss is defined using the across entropy between the predicted and ground truth matching cost volumes. For the ground truth matching cost volumes, we generate cost volumes using optical flow predicted from ground truth sharp video frames. From the optical flow map, we then generate ground truth one-hot cost volumes. As our multitask unit is light-weighted, we can stack several units to achieve high deblurring quality without too much computational overhead. By controlling the number of stacks, we can flexibly control the balance between the model size and deblurring quality. From the next slides, I will share the experimental results of the proposed network. We first show a feature incompatibility of the deblurring and motion compensation tasks. First, adopting residual learning improves the deblurring quality but downgrades the inner frame alignment accuracy. This indicates that detail-level features learned by residual learning are essential for the deblurring task but are incompatible with the motion compensation task. Second, employing motion compensation for the model without residual learning improves both the deblurring and motion compensation. In this case, as there is no residual learning in the model, the entire structure information can be used for improving the motion compensation accuracy. Then the deblurring quality also improves, following the well-known observation that motion compensation helps deblurring. However, when we naively combine residual learning and motion compensation module, the multitask detail network cannot fully exploit neither detail level nor structural features. Consequently, the model shows downgraded performance for both the deblurring and the motion compensation tasks, indicating that the two tasks require different characteristics of features. Next, we show the ablation study on the motion compensation network. When the motion loss is simply added without structure injection, it increases the motion compensation quality but degrades the deblurring quality. In this case, the motion loss induces the multitask detail network to produce features carrying structural information appropriate for motion compensation but incompatible for deblurring. However, if we employ the structure injection scheme, the deblurring quality significantly increases while the motion compensation quality is retained. This validates that the structure injection plays a key role for the multitask detail network to focus on producing detail features that can be compatibly shared by both deblurring and motion compensation tasks. The following figures show the deblurring results quantitatively compared with previous deblurring methods. We compared models on the DVD and GoPro datasets, and for both datasets, our proposed model shows state-of-the-art results, where each of our model yields an upper bound PSNR at a much faster running time. Note that our two-stacked half-precision multitask network shows real-time deblurring speed, while it shows better deblurring quality compared to previous efficiency-pursuing deblurring methods such as IFI and EST. We also qualitatively compare our model with previous ones on the DVD dataset. While our two-stack model shows real-time speed, its result is better than previous efficiency-pursuing methods such as IFI and EST, and is also comparable to previous methods employing the motion compensation task. Our 10-stack models show better restored details. The following figure shows a qualitative comparison on the GoPro datasets. Due to the severe blur in the input frames, the results of the other methods still have remaining blur. Our two-stack model removes the majority of blur successfully, comparable to efficiency-pursuing methods such as IFI and EST, despite its real-time speed. Our 10-stack model shows the best result. Here we compare our motion compensation network M with the motion compensation used in previous video deblurring methods. In the figure, column C is the alignment results of the optical flow network utilized in PVD, which explicitly computes motion between frames for constructing a pixel volume, and column D shows the alignment results of the filter adaptive convolution network leveraged in STF, which implicitly aligns temporal features for applying per pixel convolution. It is noteworthy that our motion compensation module shows much smaller model size and much faster inference speed than those of PVD and STF, while still producing moderately motion compensated results. Next, we show some video results. Thank you for listening. Please visit our website and paper for further analysis and details.